Hi guys, it's time for Chapter 2, which is about the atmosphere, its origin, composition, and structure. Our driving question is, what is the composition and structure of the atmosphere? Before we get started, I want to remind you that I'm keeping these video lectures very brief. I know it can be kind of boring to listen to a long lecture. The material is in your textbook, but I don't want you to confuse the fact that I'm keeping my lecture short with what you are or are not responsible for. You are responsible for reading the textbook and the material contained therein. As we looked at last time, the Earth system is made up of these different spheres, one of which is the atmosphere. And the atmosphere is made up primarily of gases, and then lots of little suspended particles, which are called particulates. Most of the mass of the atmosphere is located close to the Earth's surface because of gravity. So the higher up we go in the Earth's atmosphere, the less stuff there is, the less gases and the less particulate matter. Here in this table you see the primary gases that make up dry air in the lower atmosphere, so below 80 kilometers. The primary gas in the atmosphere is nitrogen, 78%. Next is oxygen, about 21%, and then just under 1% is argon, and the rest of the gases are trace gases, very small amounts. And you can see some of those, like carbon dioxide and methane. You may recognize those as greenhouse gases, and you see that their percent is very small, but their effect is very big, as we'll see later in the class when we talk more about the greenhouse effect and climate change. This table is for dry air. Another very important gas that's in the atmosphere is water vapor, but this table is not taking that into consideration because water vapor is not a constant value for space and time. It varies, and so it's hard to get an actual percentage. When we investigate the atmosphere, we use the scientific method. Atmospheric science or meteorology or climatology, these are all scientific disciplines and subject to the scientific method. I'm sure that you've encountered the scientific method in other science classes you've taken, but as a quick review, the scientific method works by first identifying some problem and then proposing an answer to that problem, which we call an educated guess. And when you state that educated guess in a manner that allows it to be tested, you have yourself a hypothesis. And what you do then is you make a prediction based on your hypothesis. So assuming the hypothesis were true, I would expect, or I'm going to predict, that such and such will happen. And then you test the hypothesis to see if your prediction is correct. And if it is, great, you can continue to test and refine your hypothesis. And if it still continues to be correct, then it becomes a scientific theory. But at any point, if your hypothesis is rejected because the prediction was incorrect, then you either reject the entire hypothesis or you will revise it. But once the hypothesis has made it through all of the testing successfully without being rejected, it becomes a theory. And a theory is simply a hypothesis that's been accepted by the scientific community. It's been subjected to the rigors of the scientific method, and it has the scientific community's acceptance. To aid atmospheric scientists in investigating the atmosphere, they make up scientific models. Models of any type, in this case they're science models, but models are just approximations or simulations of some real system. In this case, the real system is the atmosphere. So different types of models. There are conceptual models that are basically just statements or fundamental laws or relationships. An example here is the geostrophic wind model. It's a model that allows us to understand how winds behave. You can also have a graphical model, like a weather map, that shows data and information that we have in some visual way that conveys meaning. And you can also have a physical model, which is a little miniature version of a system. An example is the tornado vortex chamber at Purdue University. You can see the pictures here show the outside, the model. It's a little chamber that allows for conditions inside to simulate tornadoes so that scientists can better understand the dynamics of wind flow inside of a tornado. That's a physical model. There are also numerical models. These are very common in atmospheric science. Numerical models use mathematical equations to capture what's happening in the atmosphere. A good example is the global climate model and the rising carbon dioxide. So we want to be able to investigate what happens to our global climate as carbon dioxide, for example, increases. The model is a way for us to take into account rising CO2 levels and hold all of the other variables constant and see what the results are when the CO2 increases. What effect will that have on temperature, and how will the effect be distributed around the globe? However, these kinds of models, and all models for that matter, have errors. They're not reality, they're models. And they are only as good as the information that we have of how a system works. So it's a bit arrogant sometimes to create a model and say, I understand all of the processes that are taking place in the atmosphere, and therefore I'm able to make a model that shows what's going on. The reality is the atmosphere is very complicated, and even our best scientists with the most current information will be surprised in another short period or long period of time as we discover more information about how the atmosphere actually works. So models have that inherent error built into them. Monitoring the atmosphere is done through the surface as well as from remote sensing. Here we're seeing the automated surface observation system, which you can read about more in the textbook. This is a series of sensors, like you see in the picture here, to measure different weather variables. So temperature, wind speed, wind direction, cloud cover, precipitation, perhaps incoming and solar radiation and terrestrial radiation, and so forth. The ASOS are administered by the National Weather Service, and they are sending data to the National Weather Service servers 24 hours a day, 7 days a week. So there's a large network of these types of monitoring stations around the United States. In addition, the National Weather Service has a cooperative observer network. There are member stations that have different types of weather instrumentation. Here you see a rain gauge, which is the cylinder here, and then the Stevenson box inside of here would no doubt be temperature, perhaps relative humidity or dew point, other types of devices that need to be shielded from the sunlight. So this is a standard for collecting temperature. We also monitor the atmosphere by sending probes up into the atmosphere. We call these radiosondes, and here you see a picture of a radiosonde being launched on a weather balloon. And the information that's attached to the weather balloon you see in more detail over here. So there's a temperature sensor, and then inside the box, which has been disassembled here so you can see, there's a pressure sensor and a GPS receiver that will allow us to track the location of the radiosonde. The data that comes from the radiosonde is often plotted on a Stuve diagram like you see here that shows the height of the atmosphere. So as the radiosonde lifts up into the atmosphere, it relays its different data back to the ground. So information about wind speed, wind direction, temperature, pressure, and so on. We also monitor the atmosphere through remote sensing. And remote sensing is just any environmental measurement that is happening by some object away from the Earth's surface. So it's some remote object. And good examples here are radar and satellites, which I talked about in the Lesson 1 lecture. Here is the temperature profile of the atmosphere. A very important diagram that has a lot of information for us. Notice that on the x-axis we have temperature, in this case degrees Celsius. And up on the y-axis we have altitude in kilometers. So as we go higher up in the atmosphere, we can see what temperature is doing. And you can see the red line shows the trend of temperature through the atmosphere. And based on the different things that are happening with temperature, we can break the atmosphere into different layers. So the first layer here is the troposphere. And the troposphere is where the temperature is decreasing as we go up in elevation to about 11, 12 kilometers into the atmosphere. And we reach the end of the troposphere, which we call the tropopause. The end of each of these layers has the word pause. So the tropopause is where things start to change, and we get into the stratosphere. And with the stratosphere, the temperature stays constant for a few kilometers, and then it begins to increase up into the top. And you notice that the stratosphere is much deeper than the troposphere. But remember, most of the gases and the stuff that makes up the atmosphere is located down here in the troposphere, closer to the Earth's surface. This is where our clouds and all of our weather take place. The stratosphere is best known for the ozone layer. So there's a layer here of ozone. This is the good ozone, not the pollutant ozone that's down in the troposphere, but the ozone layer that shields us down on the Earth from the ultraviolet energy coming from the sun. That's what causes the heating effect that you see here in the stratosphere. The stratosphere extends up to just about 50 kilometers, where we reach the stratopause, and then again we have a change in what's happening with the temperature. We get into the mesosphere. In the mesosphere, the temperature remains constant for just a little while, a few kilometers, and then it begins to decrease with elevation until we reach the mesopause, and then we get into the thermosphere. In the thermosphere, you see temperature remains constant and then increases. And this, the extent of the thermosphere kind of blends into the outer edges of the Earth's atmosphere, and it really depends on if it's day or if it's night or what's happening, how deep the thermosphere is. Here's a picture of the Earth's magnetosphere, which is a sphere that is created because of the magnetism of the planet. The magnetic sphere is what prevents the dangerous solar particles from reaching the Earth. You can see its curved shape is created because of the solar wind that blows and diverts the solar particles away from the Earth. And you see this very complex structure of the magnetosphere with the inner region, the trapping region, the cusp, and the various components that you see here. But the magnetosphere protects us from a lot of the sun's dangerous radiation, especially in a year like this where we have high number of solar flares. And there's a lot of potential danger in solar flares. A lot of that energy is diverted away from the Earth thanks to the magnetosphere. The borealis, which are caused from particles ejected from the sun, and these particles get captured high up in the Earth's atmosphere. And if you are at a latitude towards the poles, towards the North Pole or the South Pole, you will see the aurora borealis like you see here. So beautiful displays of curtain-like color, typically green, but sometimes purple or various colors. That's it for lesson 2.